Hello, everyone. Today, we're going to work on our second lesson in Unit 10 on thermochemistry. This one is going to deal with phase diagrams and heating and cooling curves. So if you look behind me, this is an example of a phase diagram. This diagram shows what phase, solid, liquid, or gas, a substance would exist in based on its present pressure and temperature measurements. So for example, if we think about the carbon dioxide that we are breathing out, carbon dioxide is a gas in the atmosphere. At 1 atmosphere of pressure, where we exist, right here on our graph, we would find that at our temperature, where we are, typically about 25 degrees Celsius, so somewhere over here, carbon dioxide exists as a gas. If you were to think about dry ice, so you might have played around with dry ice when you were a kid. Dry ice is solid carbon dioxide. At 1 atmosphere, dry ice goes directly from being a solid to a gas. So that's why we never see carbon dioxide in its liquefied form. If we were to see it as a liquid, we would have to increase the pressure somewhere up here, maybe around 10 atmospheres, in order to get carbon dioxide to exist somewhere in that liquid phase. Now, we're going to identify the name that is associated with all of these different phase changes. So let's begin by looking at the change from a solid to a liquid. These names are true of any substance, regardless of what their phase diagram looks like. The change from a solid to a liquid, think about an ice cube becoming liquid water, we call that something. We call it melting. So we're going to call that change melting. The opposite of that, so going from a liquid back to being a solid, we call that freezing. The change going from liquid to a gas, sometimes we call boiling, but boiling really refers to the boiling point temperature, the temperature at which this change occurs. Typically, we're going to see that that is referred to as vaporization. And the opposite process there is known as condensation. The other two terms that we're going to talk about are the change directly from a solid to a gas, like what we see with carbon dioxide. That is called sublimation. The opposite of that process is known as deposition. Okay, I want to take a few minutes and now talk about these different points on the graph. So first of all, if we consider this point that we've labeled as the triple point. Now the term triple point comes from the fact that at that combination of pressure and temperature, theoretically, all 3 phases, solid, liquid, and gas, could coexist. So triple, because all 3 phases could coexist. Now, if you notice, there is a second point up here called the critical point. The critical point is also important because at that point, regardless of what pressure you can apply to this substance, that is always going to exist as a gas. Now, there's one last thing that I want to point out, and that is for carbon dioxide specifically, at 1 atmosphere, you'll notice that the conversion between solid and gas occurs at this temperature, negative 78.5 degrees Celsius. That is its sublimation point, the point at which it goes from a solid to being a gas. If we were talking about different substance like water, we would have 1 atmosphere at a different location in our graph. So let's take a look at what that would look like if we were talking about water instead of something like carbon dioxide. So once again, behind me, you see a phase diagram, this time for water. Once again, you'll notice that we have a solid, a liquid, and a gas. And you'll see very similar points like the triple point. Notice that this time, the line for 1 atmosphere occurs above the triple point. That's because water at 1 atmosphere could exist as a solid, a liquid, or a gas. We know this anytime that we've put an ice cube into water, we know that we're going to see both solid, liquid phases, and if we heat that up, we'll actually see it in a gaseous phase in the form of steam. So at this point, 1 atmosphere and this temperature right here, which you notice is just slightly over, this is about 0 degrees Celsius, or the freezing point of water. And this temperature right here, you'll notice if I drop a line down, is at 100 degrees Celsius, or the boiling point of water. Those points can be referred to as normal, so normal boiling point, or normal freezing point if we're talking about this temperature right here. Now, one of the things that you will notice, what makes water rather unique, is that it is more dense in its liquid phase than in its solid phase. So if we go back and we look at the diagram for carbon dioxide, you'll notice this line that separates solid and liquid is angled slightly forward. Meaning, if we take something in the liquid phase and we squeeze it enough, we can eventually turn that liquid into a solid by applying enough pressure. We're forcing those molecules close together. However, you'll notice when we talk about water, it's the opposite. So if we take water in the solid phase and we squeeze it, we will actually liquefy that water. And the reason is molecules are closer together in the liquid phase, therefore more dense, than they are in the solid phase. This is why ice floats in water. So the solid phase of water, an ice cube, is actually less dense than the liquid phase of water. Okay, let's take a look at a heating curve. So heating curves and phase diagrams are often confused by students, but they tell us 2 different pieces of information. So as we saw in the previous 2 slides, phase diagrams allow us to identify a solid, a liquid, or a gaseous phase of a substance based on the combination of pressure and temperature. A heating curve looks at a single pressure and then measures what temperature and how much energy must be added to go from a solid to a liquid to a gas. The difference is heating curves also expand on the phase changes. So what was just a line on a phase change diagram, we now see is a much more important piece when we're talking about a heating curve. So that process of melting or freezing occurs over a period of time and with a tremendous amount of energy. The same can be said for the process of evaporation or condensation, which again is a much larger and more significant piece of this graph than was previously identified in our phase change diagrams. Now, these graphs are what we're going to use in some of our calculations today. We're going to be looking at the amount of energy required to bring a substance from one temperature to another. One of the things that we're going to have to pay attention to is whether or not that substance would go through a phase change. So, for example, if we're taking a sample of water from 10 degrees Celsius to 110 degrees Celsius, we're going to start off somewhere down here where water is a liquid. We're going to heat up to the boiling point of water. We're going to go across and change all of that water, which was a liquid on this end, to a gas over here. When a substance goes through a phase change, it stops changing temperature. And instead, what that energy is being used for is to break those bonds that hold those molecules together in the liquid state. If you think about what a liquid looks like compared to a gas, where the molecules are spread really far apart, we have to break all of those bonds in order to separate those molecules and drive them apart from each other. So during that process, the process of vaporization, or as it says in this diagram, evaporation, energy is not being used to raise the temperature of the water. Energy is being used to break those bonds between water molecules apart and separate them from each other. The same could be said during the process of melting. So we're breaking those bonds and allowing those water molecules to slide past each other in the liquid phase. The phase changes occur at a constant temperature. Now, that becomes a problem for us. Why? Because our equation, Q equals mc delta T, is always going to equal 0 if the temperature is not changing. So instead, we needed to come up with another form of the equation that would allow us to calculate the amount of energy absorbed or released during a phase change. And that's where we came up with these two equations. Q equals mass times delta H of fusion, and Q equals mass times delta H of vaporization. Those constants, delta H FUS, which stands for fusion, or delta H VAP, which stands for vaporization, are ways for us to calculate the amount of energy absorbed or released, even though temperature is not changing. The one thing that I want to point out to you is this. If you notice, we use fusion down here when we're talking about melting and freezing. We use heat of vaporization over here when we're talking about vaporizing, going from a liquid to a gas, or condensing, going from a gas to a liquid, that same substance. Notice how much larger this amount of energy is compared to this one. That means it requires a lot more energy to take the same amount of water and convert it to a gas from a liquid than it does to convert it from a solid into a liquid. So let's take a look. So the first question says, how many joules of heat are given off when 25.0 grams of liquid water is cooled from 10.25 to negative 17.65 degrees Celsius? Let's take a look at our heating curve. So it may help if you just sketch out a quick heating curve when you're ready to do these problems. So if we're talking about water, the first plateau that we see here is at 0 degrees Celsius. The second plateau that we see up here is at 100 degrees Celsius. So it might help to mark off where your change is occurring on your graph. So in this case, I'm going from 10.25 degrees Celsius, that's somewhere around here, down to negative 17.65. That's way down here. So we're going in this direction from a hotter temperature to a cooler temperature. So remember what we learned in our last lesson. Anytime we're cooling, we're releasing energy. So all of our values for Q in this problem are going to have negative signs in front of them. Let's take a look at this first part. So going from our starting point, 10.25 degrees Celsius, down to this point is a difference of 10.25 degrees Celsius, right? We're going from 10.25 down to 0. So during this portion, we're going to use Q equals mc delta T. They tell us in the problem that we have 25 grams of water. We're going to use our constant for water as a liquid, which is 4.18 or 4.184 joules per gram degrees Celsius. And we're going to multiply that by our change in temperature, which in this case is 10.25 degrees Celsius. We cannot simply subtract the two temperatures when we're going through a phase change like we did in lesson 1. Because energy is used differently, depending on whether you have a liquid, whether you have a solid, or whether you're going through a phase change, we have to break this up into 3 separate parts. So the first part, which is the one that we're working on right now, we're going to get a Q value. Remember that we said it's going to be negative because it's cooling down, and it's going to have a value of 1,071. We'll just round it to the nearest whole number, 1,071 joules. That is not the final answer to our question. In fact, that's just part 1 of 3 different parts. In part 2, which is this part right here, we're going through our phase change. Now remember, we said earlier, when we're going through a phase change, we're not going to use this equation. We're going to use this equation, mass times delta H. And in this case, remember, this is for melting and freezing. This is for vaporizing and condensing. So if we look, we're going to use the one for fusion. That's the one that you use when you're when you're freezing. So in this case, we're going to have 25.0 grams. The mass of water is not going to change throughout this entire problem, times our constant, which is right here, 334 joules per gram. So 25 times 334, we get an answer of negative, again, because it's freezing, it's going in this direction to the left, 8,350 joules. Finally, the last part. So now that we have taken our liquid, converted it from a liquid to a solid, now we're lowering the temperature of that solid. So part 1, part 2, and now we're going to take a look at what we're going to call part 3. We'll do that part down here. Temperature is once again changing. So again, we can use Q equals MC delta T. The only time we can't use that is when we're going through a phase change and the temperature stays constant. What doesn't change is the mass of water. That's going to be the same throughout the entire problem. In this case, because now we are looking at water as a solid, we have a different value for C when water is a solid. So in this case, it is 2.09 joules per gram degrees Celsius. And finally, our temperature change, which started off at 0 and has now dropped down to negative 17.65, that's a change in temperature of 17.65 degrees Celsius. So I can type all of this into my calculator. So 25 times 2.09 times 17.65. So I get a value for Q. Once again, Q is negative, 922 joules. Once you have completed all parts, in this case it was 3 parts, but it could be as many as 5 parts. Once you have completed all parts, you're going to add together all of your values. So we're going to add together 1,071 plus 8,350 plus 922 for a total. So Q total is still going to be negative because we're cooling, 10,343 joules. Okay, that's problem number 1. pretty straightforward, but let's keep going. Let's take a look at a second problem. Again, these problems, once again, are part of your homework assignment. So if you open up your homework assignment, you can go through and complete these problems as we finish them together here, and then just finish up whatever we don't go over for homework. Okay, in problem number 2, it says how many joules of heat are needed to change 15 grams of liquid water at 100 degrees Celsius to steam. So we're going from, here's our phase change diagram. We're starting here with water as a liquid, and we're changing it to right here, water as a gas. This is convenient. It's only going to be a one-step problem. And because we're going from liquid to gas, we're putting in energy, our value for Q is going to be positive. Now, because our change in temperature is 0 when we're going through a phase change, we're not going to use Q equals MC delta T up here or any of these values. Instead, we're going to use Q equals mass times heat of vaporization. In this problem, they tell us that we have 15.0 grams of water, and our constant for the heat of vaporization is going to be 2,258 joules per gram degrees Celsius. So typing this part into our calculator, we have 15 times 2258. One step problem again, we wind up with a final answer of 33,870 joules. Remember, I said in lesson 1, don't be surprised if you end up getting values for Q that are in the tens of thousands, even hundreds of thousands. Okay, we're going to do one final problem together. So if we look at this final problem, it says we have 75 grams of ice at a temperature initially of negative 15.25 degrees Celsius. We heat that until all 75 grams of it become gaseous water, or steam, if you will, at 103.75 degrees Celsius. And it wants to know how many kilojoules, so we're going to calculate it in joules first, then we'll convert it to kilojoules at the very end. How many kilojoules are needed to do this? So once again, I'm going to start off by drawing a heating curve so we can follow along and identify how many different parts to this problem we have. So in this problem, we're starting off at negative 15.25 degrees Celsius. That's way down here. Then we're going to go up to our freezing point, our melting point, 0 degrees Celsius. That's one part to the problem. We're going to melt all of our ice. That's part 2. Then we're going to take our water, which is at 0 degrees Celsius, and raise its temperature up to 100 degrees Celsius, liquid at 100. That's part 3. Then we're going to take our liquid at 100 and convert it to a gas at 100. That's part 4. And then finally, once we have all of our gas at 100, we're going to finish off up here at 103.75 degrees Celsius. So this is an example of a 5-part problem. I'm doing this on purpose because this is as difficult as I can possibly make a problem. So I'm going to walk you through this. Okay, for the first part, down here where we see part 1, temperature is changing. So whenever temperature is changing, we can use our equation Q equals MC delta T. In this case, in fact, throughout this entire problem, our mass is going to be 75.0 grams. we're going to use the C value, the constant value for water as a solid. And I'm going to label them over here as we use them for each part, because we're eventually going to use all 5 of these. So for the first part, we're going to have 75 grams times 2.09 joules over grams degrees Celsius times our change in temperature. Well, going from negative 15.25 up to 0 is a change in temperature of 15.25 degrees Celsius. Because we're adding energy throughout this entire process, as we go from down here all the way up to 103 degrees Celsius, all of our values for Q are going to be positive. So typing this into our calculator, we have 75 times 2.09 times 15.25. We get an answer of 2,390. Now, 2,390 joules. That is our answer to part 1 of 5. Now let's take a look at part 2. So in part 2, we're now going through a phase change. Phase changes mean temperature is not changing. That means we can't use this equation. We have to instead use Q equals M times delta H. Because we're talking about melting, remember that's over here with fusion. So we're going to use delta H FUS. And this is the constant that we're going to use for this equation, 334 joules per gram. So once again, we're going to take our 75.0 grams. We're going to multiply it by our 334 joules per gram, 75 times 334, and we get an answer of 25,050 joules. This is our Q value for part 2 of the problem. We have now gone from a solid at negative 15.25 up to 0, now across from all solid to all liquid. We're now ready to look at part 3. So in part 3, we're once again changing temperature. So we're going from water at 0 degrees up to water at 100 degrees. So for part 3, we have Q equals MC delta T. Our mass is going to remain a constant at 75 grams. This time we're using the C value for water as a liquid, the 4.18 joules over gram degrees Celsius. And our temperature change, because we're going from 0, where we melted all of our ice into liquid water, up to 100, that's a difference of 100 degrees Celsius. Typing this into our calculator, 75 times 4.18 times 100, we get 31,350 joules. Again, Q is positive because we're adding in energy. Okay, so now we've done steps 1, 2, and 3. We're ready to look at step number 4. Step number 4, you'll recall, is another phase change. So once again, we cannot use this formula. We have to use Q equals mass times delta H. This time we're going to use the delta H of vaporization, so VAP. We'll have 75 grams times our constant 2,258 joules per gram. So our value for Q, which again is going to be positive, 75 times 2258, is going to be an enormous number, 169,350 joules That is our Q for part number 4. I'm just going to add this in. Part number 1, this was part number 3, this is part number 4. This value for Q was for part number 2. In our final piece, we are now here. And we are trying to get to here, this final temperature of 103.75. Because temperature is changing again, I can go back to using Q, M, C, delta T, 75.0 grams. This time, the constant that I'm going to use is this constant for water as a gas. Notice, for these 3 constants, you use them when temperature is changing. For these 2 constants that are down here, numbered 2 and 4, use those for phase changes. So I'm going to use the 2.01 in this case. And my temperature change for this last leg is just going from 100 up to 103.75. So my temperature change is only 3.75 degrees Celsius. So typing this into our calculator, we have 75 times 2.01 times 3.75. And in this case, we get an answer of 565 joules. Believe it or not, when you get to this point, you're ready to bag it, but you got to do one last step and you have to add together all of these different pieces. So we're going to take our answers from part 1, from part 2, 3, 4, and 5, and add them all up to get our total answer. So we have 2,390. That's from part 1. From part 2, we have 25,050. From part 3, we have 31,350. From part 4, we have 169,350. And from part 5, we have 565 joules. That brings us to a grand total. So Q total equals 228,705 joules. Now, this problem specifically asks for an answer in kilojoules. So even now, we have to do one final step and just divide. So there are 1,000 joules in 1 kilojoule. So we're going to take this number, divide it by 1,000. So we're going to get 228.705 kilojoules, or we can round this to just 229 kilojoules. Seems like an awful lot of work to come up with such a simple answer of 229 kilojoules. Okay, you have just 2 homework problems tonight to try on your own. I will post the answers to those homework problems so you can have a look at them. Please let me know if you have any questions. Send me a message through email or through Schoology, or stop by office hours. Thanks, everyone. Hope you had a great week.